world. Now I will be able to discuss the water-steam relationship uh, in thermodynamics calculation. Okay, so in here also we need to account the pressure, temperature, enthalpy, okay, the entropy, like that, specific volume, like that. So we are be able to use the saturated steam and saturated water temperature based steam table, and also the saturated steam saturated water pressure based table, and then also the superheated, okay, and sub cold steam and water, like that. Okay, so I have here, okay, here water steam, okay, at pressure of 0.01 megapascal, saturated temperature of 45.806 degrees Celsius. This one. We will be using this somewhere along our computation. But of course, we need to take note the given temperature and pressure. If it really matches to this, then we will use this table. Okay? And then we have also the saturated water and steam, temperature based. This one. So if our problem will stay the temperature, then we can use this table, the steam table for temperature based. And we have also the uh, steam table, the pressure based. So we can really detect because in our question or in our problem, it involves only pure substance water, no other thing. Okay, this is entirely different because previously or in my past discussion of thermodynamics, we discussed a lot of inorganic liquids, okay, organic liquids, or any chemical reactions. But in here, this is different because this is really pure water only. That's why we need to use the steam table. Okay, so if the chemical reactions or the given in the problem is not water, or it's not steam, or there's no such like that, then do not use this one. Okay, very clear. So this is only exclusive for relationship between the water and steam. That's why we have steam table, where we can really, feel the problem. Okay, what's all about. So in here, we have a specific volume, a specific enthalpy, a specific entropy, a temperature-based steam table, and a pressure-based steam table, something like that. And here also, uh, we practice the interpolation, okay? Interpolation on how to determine the specific enthalpy, especially temperature that is not really specific here, okay, the in between the given there and it's not found, then you have to use the interpolation by using the slope technique in algebra, like that. Okay, as you can remember the one x, okay, x1 over x2, y2 over y2, something like that, and then x2 minus x1 over, like that. Okay, okay, x1 minus x2 minus x1, okay, over something like that, x3 minus x2, or y2 minus y1 over y3 minus y2, something like that. Or we can say x minus x1 is equals to x2 minus x1, or is equal to y minus y1 is equals to y2 minus y1, something like that. Okay, it depends on our graph of the interpolation, but we have short technique for that, no need to graph. Okay, something like that. So this is an overview, and of course before going to problem solving, as I said, we will be able to use this one. Okay, but I have to introduce the formula that is very necessary to uh, start solving those thermodynamics problem which relates to steam and water relationship, okay, by using steam tables. Okay, right. So the first formula will be based on volume. Okay, this is only uh, steam and versus water relationship, huh? Okay, steam versus water relationship, meaning there's a change of states from liquid to gas, or shall we say liquid to vapor during evaporation, something like that. So I think also there's no other process here. There's no condensation, there's no sublimation, there's no deposition. Because yesterday I discussed a lot of phase changes, right? But here focus only on evaporation and vaporization. Okay, but still the concept I discussed a while ago or previously will be used here also, but specifically for the evaporation and vaporization, which is the latent heat of vaporization. Okay, like that, or heat of vaporization or enthalpy change of evaporation will be applied also here, especially in the stable. Okay, now we have the formula to be used. Just memorize this directly in a way. Uh, it's not very difficult, right? We have volume is equal to the final volume of a liquid, okay, plus, okay, here we introduce another fraction. In chemistry, we have the mole fraction, the pressure fraction, the volume fraction, but here we have the dryness fraction, x times Vg, this one. Okay. This is the first formula to be introduced, our overview formula for steam and water relationship at saturated temperature, at saturated pressure. When we mean here of steam table, like the saturated temperature, saturated pressure, okay, and also superheated vapor, okay, so high pressure and high temperature already. Okay, so total volume is equals to Vf, means volume of the liquid. So this is the volume at the liquid state of water. So we represent F as liquid. Okay. And G as gas or vapor. Okay, class. This is F stands for liquid, and then G stands for gas and vapor. But actually, I don't like the symbol because I want this to be L supposedly, right? Because it's liquid. That's okay. Just really remember that F stands for water here in this discussion, specific discussion. Okay, so total volume is equals to, okay, the specific volume of the liquid. This is specific volume, not the volume only, specific volume. Okay, plus the dryness fraction, okay, times the volume of the vapor or volume of the gas. Okay, now what is specific volume? Specific volume it is a volume occupied by a substance, okay, in terms per kilogram or per gram, like that. Okay, specific volume, it is an amount of volume occupied per mass of a substance. Okay, so that means the unit will be cubic meter per kilogram. Okay, specific volume is equal to cubic meter per kilogram. This is the amount of volume per amount of the mass. So this is here in this corner, these are all specific volumes with the liquid and the gas, not the mass alone. Okay, so if we mean mass alone, then we need to multiply this specific volume. Okay, if we talk about volume alone, sorry, we need to multiply the specific volume to the mass so that it will be cancelled, and we have now the volume alone with its cubic meter. So if this is the specific volume, this is also the specific total volume, something like that. Okay, then if the problem will state what is the total volume of the tank, then you have to multiply the total amount of mass that is inside the tank, okay, which is normally the water. Okay, like that. Okay, Because if you answer really the total specific volume also, it will be wrong because it still have the unit like this. And we are now finding the total volume of the tank. So we need to multiply the total mass of water inside the tank. So calculate the total volume of water inside the tank. By using this formula, then we need to multiply this by mass, our specific volume or our total specific volume. Okay, now our x. So in here, specific volume, so the reverse will be exactly that. Okay, the density. Okay. Okay. Okay, guys. Specific volume, okay, cubic meter over kilogram, and the reverse of the specific volume is the density. So we have now another definition of density. Before in physics and chemistry, we know that density is equal to mass over volume, and now we have also density is the reciprocal or the reverse of specific volume. Okay, density is the reverse or the reciprocal of the specific volume. And now we go to the x here. Okay, x or dryness fraction is equal to the mass of the gas or the mass of the vapor over the total mass, in which mass is equals to mass of the vapor or a gas plus mass of the liquid. So we have the dryness fraction, we have the mass of the gas or the vapor over the total mass, okay, of the entire water. So our total mass of the water or pure liquid water is equal to mass of the water in gaseous phase and mass of water in a liquid phase, M, G, and F here. Okay, like that. Something like that. So this is gonna be like this. Okay, now something like that. Okay. So our VF, like, sorry, this is really not VG alone, this is VFG, ha, because this already the total change man siya, because there's a combination of the dryness fraction naman siya. Okay, sorry for that, I beg your apology, because this is the dryness fraction. If this is the dryness fraction, we are taking into account the vapor state and the liquid state. So this is automatically the specific volume of the liquid and the gas here, VFG. I put first initially the specific volume of gas alone, right? And I came to think, oh my god, there's no other value. Say this is already a combination man. Okay, so this is VFG. Sorry for that. Okay, so VFG. Okay, so this is our VFG here. I corrected already, right? Because this is a combination of liquid and vapor statement siya. Okay, here. So VFG is equals to the specific volume at a vapor state minus a specific volume at the liquid state. So this is our VFG. Okay? VFG or the specific volume, okay, during evaporation, change from liquid to gas, FG, okay, is equals to the specific volume of the vapor or the gas minus the specific volume of the liquid, which is F, something like that. That's why I corrected that here immediately, because I analyzed this portion here is a sort of combination between the liquid and the vapor state, okay? Something like that. And now if this is not enough, okay, we need to simplify this by using algebra. Okay, so we can say this as V is equals to Vf plus X Vf Vg. This one. Okay? V is equals to Vf plus V, okay, or X Vf Vg. Okay, here. This means Vf Vg. So I split that here. So we can simplify that here also. So we have V is equals to Vf plus XVF, okay, like that, plus XVG, like this in algebra. V is equals to Vf plus XVF plus XVG. And now transposing the common, so V is equals to, okay, XVG, okay, plus XVF, okay, plus VF, like this, okay. Okay, and doing the algebra is equals to V is equals to XVG plus VF X plus 1. Okay, like that. Tama ba? This one. Okay. So, again, we need to simplify like that. XVG plus XV. So, XVF, XVG, then VF. So, XVF. Okay. And then XVG plus VF. So, X. Okay. Then XVF, XVF, XVG. Then XVG, XVF plus VF. Okay. And then, okay. And then we have XVG minus VF, like that. Okay. And then we have XVG. Okay. The common here is X. Okay, so XVG plus VF is equals to VF, right? Then XVG, XVF, okay, VF is equals to V, like this. Simplify. Okay, you can simplify doing the algebra, and then we can get, okay, we can get V is equals to 1 minus X times VF plus XVG, like this. Okay, so we now obtain the, this value upon doing the mathematics. Okay, V is equals to, okay, 1 minus X times VF times XVG. This one is formula. Another formula also aside from this formula here. We can use also this and also this. It depends. Okay, like that. Okay, and then we need to use another formula also, which is the, okay, specific enthalpy is equals to enthalpy at the vapor state, okay, and then plus enthalpy at the vaporization stage. This one. This is the enthalpy. Specific enthalpy is equals to the enthalpy of the liquid state plus the enthalpy at the vaporization state. Okay, actually it is derived from, okay, HF plus HG is equals to HFG, right? Okay, like this. And then HFG is equals to HG minus HF. Sorry, this one. This is specific enthalpy for specific enthalpy. H alone is equals to the specific enthalpy at liquid state of water plus the specific enthalpy of the vapor state of water. So this is the specific enthalpy, the H without subscript. Now, why we obtain this one? Because of this one. Okay, through the theory of latent heat of vaporization, from a change from a liquid, which is F, to the gas, we have the latent heat of vaporization of the gas or the product minus the latent heat of vaporization of the liquid reactant, something like that. Okay, okay, so that's, so you solve the here. Okay, when you solve the, okay, H gas here, okay, like that. Okay, so we have the latent vaporization from the state of liquid to gas is equals to, okay, is 1. Okay, the gas state minus the liquid state. Then if you solve for the enthalpy for the gas state, Hg, okay, will be equal to this one. So literally, this H here is a specific enthalpy of liquid in a vapor state. Okay, like that. And this is the latent heat of vaporization from liquid to gas, and this is the specific enthalpy during vaporization, and this is the specific enthalpy at a liquid state of water. Again, okay, specific enthalpy during the vaporization of water is equal to the specific enthalpy of liquid state plus the specific enthalpy during vaporization. And this specific enthalpy during vaporization is equal to the enthalpy at the gas state or vaporization state minus the enthalpy during liquid state. That's why when we solve the H gas, because specific enthalpy at the vaporization state is just equal to Hg. Okay. Hg. Okay. Like that. Okay. Hala. Okay. So our Hg is just equal to H. The specific enthalpy, okay, during vaporization, H is just equals to the enthalpy at the vaporization state, which is a gas. This one, H, and this one. Okay? And so we obtain this one. It's coming from here, latent heat vaporization. Okay? So the same thing also with the entropy. Entropy is equal to the entropy at the liquid state. Okay? Okay, plus the entropy at the liquid state to gas. Same thing. This one, entropy. The same thing with entropy also, huh? Entropy is equals to the entropy of in the vaporization state of the water is equals to the entropy at liquid state plus the entropy of water, a change from liquid to vapor or gas. It's the same thing. Okay. Now, if we need to involve the dryness fraction, then the formula will be the same with this here, here, okay, or here, here. So you'll just substitute the value like this. It will become H HF plus X HFG, something like that, okay? And then S is equals to SF plus X HFG. So like this. So this is now our new formula. So equation 1, this one, equation 1, this is equation 2, and this is equation 3. This one, equation 4, this one, here, Greenwich fraction, equation 4, and we have equation 5 here. But equation 5 is not usually used because we have already the value, as we have a temperature based value, the pressure based value of the same table. Then we no longer get the the specific volume at the vaporization state from liquid to gas. The same here also, because the HFG is always given in the steam table here. Okay. Again, the specific volume of the vaporization state from liquid to vapor or liquid to gas are already given here. The HFG, VFG, and SFG. So instead of having the volume, which is VF minus VG, or some specific volume, specific enthalpy also, HG minus H liquid, okay, entropy also, SG minus SF, okay, it's already given here, okay, the specific enthalpy, specific volume, and specific entropy. So there's no problem anymore because it's here already. All you have to do is to analyze a little bit, okay, and then substitute values, okay, like that. So thank you so much for watching this short live stream regarding water and steam at saturated temperature and pressure and superheated water and steam, okay, like that, by using steam tables. Okay, thank you so much for watching this video, and I hope you can click the notification bell for some newest updates of everything internal. Sa pinandila. Bye bye, God bless everybody. Cut.